Alright, hi everyone, welcome back. In today's video, we want to have a short video, but we're going to go interplanetary with 3 deviations, and we're going to discuss Kepler's laws of planetary motion. Now, I'm not going to go into many examples with this. This is more just an interesting, palate cleanser to what you can do with these vector functions in terms of physics and how you can model things with vector functions. They're very, very, very useful for modeling our world. Now, Kepler's laws were developed by a man with the last name of Kepler, and he went off of some of Newton's principles in physics in order to generate some ideas about how planets move around stars, right? So in our solar system, we have about 8 planets, 9 if you count Pluto, that orbit around the sun. And many people thought originally that they did so in circles. So if I have the sun here, then the planets move around in concentric circles, like so. And they move around with uniform circular motion that you can easily learn in elementary physics. Now, that's fairly useful to modeling the solar system if we only need to use uniform circular motion. However, things are a little bit more complicated. It turns out that they do not move around in circles. They move around in other ellipses, and ellipse is another type of a conic section. It turns out a circle is just a degenerate form of an ellipse. So, in fact, the ellipse is the more general case. So you could have an elliptical orbit that might just happen to be a circle. Anyways, let's get into this. So I'll just look at the 3 laws today. So a planet the first law says that a planet moves around a star in an elliptical orbit with the star as a focus. So now if we remember what an ellipse is, I have an ellipse, draw a vertical ellipse maybe, really bad vertical ellipse. I tend to sketch things, it makes things a little bit less horrible. But anyways, if I have an ellipse, I have a major axis, I have a minor axis, and then I have along the major axis, I'll have a focus, I'll have a pair of focus, plural of that is foci, however you like. And anyways, the idea is that the distance between the 2 focuses that touches this edge of the ellipse. So if I have this here, this total distance between the 2 foci that touches the edge of the ellipse is always the same. Now, the idea is that if I have a planet, if this is a planet, then this would be a star. So this would be a star, and it would rotate around the ellipse with one of the stars as a focus. And so it can be proven that because forces are only acting on the planet with radial and tangential accelerations, there's no acceleration into the blackboard. So there's no 3-dimensional component. So we're essentially dealing with 2-dimensional or 1-dimensional motion along an ellipse, and there's no variation in height because there's no forces that are acting in that direction. Now, additionally, another one of Kepler's laws says that equal areas are swept out in equal times. So if I have an ellipse, like that, and I have my star here, and my planet moves from here to here. My planet moves from here to here, and here I have an area A. And then my planet also moves from here to here. And then that's also an area A. So these are both equal areas. That means that the time to go between there and there, t, is equal to the time to go between there and there, so t. Right? And we can make this, we can make these infinitesimally small, and then we can make these vectors to make up triangles. And that makes it easy to calculate those. Now, finally, I would like to say the third law is the square of the period is proportional to the cube of the major axis. So if I know the major axis value, we'll call that value r, and I know the period t, then t squared is proportional to r cubed. And that's the third law of Kepler. And then I'll just preface this by, or well, not preface, I'll end this video by just going over some of the fundamental equations that govern what we do for Kepler's laws. The first one is the conservation of energy. So if I have the energy at an initial point and I have the energy at the end point, those energies are equal. The force due to a gravitational source is equal to the gravitational constant g times the product of the two masses in the system divided by the square of the distance between them. You can make these vector quantities by adding a unit vector to the end of this, or vector quantity at the end of this. And then we could also find the gravitational potential energy by integrating and taking the negative. So we integrate this, we take the negative integral, and we take that with respect to r. This is easy. Here we get the potential energy, which I call V. It's equal. Now if I take the integral here, I will get negative 1 over r times gmm plus gravitation, or plus constant. So what's important about that is something that's very, very neat. It's that the force is equal to the negative derivative of the potential. And we're going to make that a lot more generalized in multivariable calculus when we discuss gradients and partial derivatives, because force might depend on other variables and not just x. All right, so that is Kepler's laws and some of the major equations governing Kepler's laws. In the next video, we're going to introduce multivariable functions. There will be a new unit, Unit 3. All right, we'll see you in the next one. Bye.